You know that feeling when you first unbox a brand new phone or a fresh laptop,
Oh, yeah. Best feeling.
right? You boot it up and it is just lightning fast. Every app snaps open instantly. The battery lasts forever. You feel like you're holding, pure magic.
Right.
But then like a year goes by, maybe two, and suddenly, for reasons you cannot possibly explain, you're staring at a spinning wheel just trying to open your email.
Yeah, the honeymoon phase is over.
Exactly. The hardware hasn't changed. But the entire system has just become inexplicably sluggish, and you have absolutely no idea why.
Well, it's basically the universal law of digital entropy. Systems naturally degrade over time, right? Unless you actively maintain them.
Yeah.
They just accumulate all this hidden weight, these invisible processes and tiny redundancies. And on their own, they mean nothing. But together, they act like a massive anchor just dragging the whole system down.
And I mean, this doesn't just happen to our personal laptops, which is what we're talking about today. It happens at the absolute highest levels of software engineering, where, frankly, the stakes are massive.
Oh, absolutely.
So today, we are focusing our deep dive on a huge bottleneck in the software development world, and that is continuous integration systems getting incredibly bogged down.
Yeah, the CI pipelines.
Right. And if you aren't familiar with the term continuous integration, or CI, it's essentially the automated factory floor of software development.
That's a good way to put it, yeah.
Like every single time a developer writes a new piece of code, the CI pipeline compiles that code and runs, I don't know, thousands of automated tests to make sure the new code didn't break anything else in the system.
Which, is a brilliant safety net in theory.
In theory.
But the problem we're seeing across the entire industry right now is that these CI pipelines are taking longer and longer to run. Like a process that used to take 5 minutes now takes 2 hours.
Which means developers are literally just sitting around waiting for their code to pass. It's costing companies an absolute fortune in idle time and server compute costs.
Yeah.
And here is the real kicker. The test suites are taking longer to run, but the actual quality and safety of the software isn't improving at all.
The safety net is just getting heavier. It's not getting any stronger.
Exactly. So to figure out what is going on here, we've got some fascinating source material today. It's anchored by a presentation from 2026 by a developer named Luck036. And it's titled Systematic C++ Test Suite Maintenance, Dedup, and Gap Fill.
And I have to say, this presentation is a masterclass in managing information bloat. Not just for C++ code, but in general.
Yeah, it really is.
It forces us to look at this massive hidden tax we pay for unchecked generation in the modern era.
So our mission today is to explore this wild paradox at the center of the presentation. Because look, the tech world brought artificial intelligence coding agents into the mix to make developers vastly more efficient. But this source material makes a really compelling case that AI agents are actually the primary culprits causing this massive system bloat.
Yeah, it's totally ironic.
It is. And after we figure out why the AI is breaking things, we're going to unpack this brand new agentic skill designed to ruthlessly and safely delete redundant code. But okay, let's unpack the first part because I find this irony incredibly rich. How is the AI, like the ultimate efficiency engine, causing a traffic jam in the code base?
Well, it really comes down to a fundamental misalignment in how AI agents operate compared to, human developers.
Okay.
The very traits that make AI so astonishingly good at generating code, the fact that it's fast, it's thorough, and it's tirelessly additive,
Yeah.
those are the exact same traits that make it an absolute nightmare for long-term system maintenance. The author, Lug036, identifies 6 specific reasons why AI creates this test bloat. And they basically all stem from the architecture of how these agents process context.
Right. The presentation outlines these 6 blind spots.
Yeah.
And the ones that really stood out to me were prompt-driven amnesia combined with cross-session blindness.
Yeah.
But I struggle to understand that. Like, how can an AI that supposedly has access to a company's entire code base be blind to what's already there?
Well, that is the illusion of AI. We assume it has this omnipresent understanding of the whole code base.
Right. It read everything. Right.
But it hasn't. Not all at once.
Ah.
When you spin up an AI agent for a coding task, you're opening a specific isolated context window. So let's say you have Agent A.
Okay.
A developer tells Agent A to write some tests for a new checkout function in an e-commerce app.
Got it.
Agent A does a great job, creates a file called testcheckoutbasic.cpp. But then 2 weeks later, a completely different developer spins up Agent B and asks it to write tests for edge cases in that exact same checkout function.
Oh, and Agent B has no memory of Agent A ever existing.
Precisely. Unless the developer explicitly loads Agent A's specific test file into Agent B's context window, which honestly they rarely do because they're just trying to move fast.
Right.
Agent B just starts from scratch. It has cross-session blindness. So it writes a brand new file, maybe called test checkout advanced.cpp, which inevitably overlaps with and duplicates the basic tests Agent A already wrote.
Okay, let me see if I have the mechanism right here. It's like having a roommate who has zero short-term memory.
Okay, I like that.
Like, it's not just that they're careless and they don't check the pantry before they go grocery shopping. It's that the second they walk into the store, their memory of the apartment is totally wiped clean.
Yes.
All they have is the sticky note you handed them that says, buy ketchup. They have no context that they bought ketchup yesterday or the day before, so they just keep buying it. Every time you send them, they execute the prompt perfectly.
That is an excellent way to visualize it. They only know the immediate prompt. And, this leads directly to another flaw the source highlights, which is the additive reflex.
The additive reflex.
Yeah, an AI is a generative engine. When prompted, its instinct is to add. It never pauses to audit. It never says, hold on, let me run a search script across the repository to see if someone already bought ketchup.
Right, which brings up the next blind spot, coverage gap blindness. Because, a human developer usually runs a coverage tool before they write new tests. They look for the holes in the safety net.
Exactly.
But the AI just looks at the source code, sees a list of 50 functions, and starts writing tests for all 50, completely blind to the fact that 45 of them are already safely tested elsewhere.
And we really have to look at the incentive structures built into the underlying language models here.
What do you mean?
Well, these models are inherently people pleasers. They are rewarded during their training phase for providing comprehensive, voluminous answers.
Ah, right. More is better.
Exactly. If an AI writes a massive 50-page test suite, its internal mechanics recognize that as a highly successful completion of the prompt.
But surely the developers who build these AI tools could just train them to be efficient, right? Why don't they give the AI a reward for realizing a test is redundant and just skipping it?
Because proving a negative is so much harder for a language model than generating a positive.
Wait, really?
Yeah, think about it. To safely skip a test, the AI would have to run complex compilations and logic checks that fall way outside standard text generation. So the AI develops absolutely no removed muscle.
Huh.
It has a robust function to write code and maybe a decent function to edit code. But the act of removing a file entirely to an AI that literally feels like failing the prompt. It goes against its fundamental programming to produce output.
So we basically have these highly motivated, memory-wiped AI agents hoarding ketchup in our code bases. They're generating thousands of automated tests that check the exact same logic paths over and over again. And every time the human developers try to release a new feature, the CI pipeline has to compile and run all those overlapping tests, which is why the system is grinding to a halt.
You nailed it.
So how do we teach the AI to clean up its own mess? Because this is where the presentation introduces the DEDUP workflow.
Right. And this workflow requires us to completely redefine how we think about redundancy.
Okay, how so?
Well, usually, if a human sees two things that look conceptually similar, they consider them redundant. But the core insight of this presentation is that true redundancy in software testing is not about similar concepts. It is strictly, mathematically, about identical values and identical execution paths.
I'm going to push back on that because that feels, overly pedantic.
Okay, let's hear it.
Let's say I have an application with a basic calculator function. I have test A, and it checks what happens when you add 2 plus 2.
Right.
Then I have test B, and it checks what happens when you add 2 plus negative 2. Conceptually, they are both doing the exact same thing, testing the addition function. If my CI pipeline is totally bogged down, why can't I just have an AI look at those, say they look similar enough, and delete test B?
Because you would be introducing a massive hidden risk into your software.
Really? Just from that?
Yes. In computer science, different inputs trigger entirely different microscopic pathways within the code. Adding 2 plus 2 is a happy path. It's simple.
Right.
But adding a negative number might trigger a completely different block of error handling logic, or it might require the system to allocate memory differently under the hood.
Ah, okay.
Yeah.
So even though the tests look nearly identical on the surface, test B is acting as a safety net for a completely different hidden mechanism.
Exactly. When a test runs, it frequently uses things called assertions. For those unfamiliar, an assertion is essentially a tripwire built into the test.
Tripwire.
Yeah, it's a strict rule that says, at this exact microsecond of execution, This variable must equal exactly this value.
And if it doesn't?
If the variable doesn't match, the tripwire snaps, the test fails, and the developer is alerted to a bug. So if you let an AI delete test B just based on the vibe that looks conceptually similar to test A, you just removed a critical tripwire.
Oh.
The next time a developer accidentally breaks the negative number logic, no alarm will sound because you deleted the only test that walked down that specific path.
Okay, I get it now. So two tests are only truly redundant if they feed the exact same identical values into the system, forcing the computer to walk down the exact same logic path and trip the exact same assertions.
Precisely. You cannot just unleash a large language model and say, hey, delete the duplicates. It will hallucinate and delete vital safety nets based on surface level similarities.
Right, because it doesn't actually understand the code.
Exactly. And that is why the author, Lick036, built this multi-phase agentic skill, a meta-correction tool that doesn't just read the text, but actually compiles and runs the code to mathematically prove redundancy.
Yeah, the presentation breaks this down into this intricate workflow from phase 0 to phase 5. Phase 0 seems to be the simplest part, right? Identifying the suspects. The system scans the repository looking for file names that suggest overlap. Like if it sees testshoppingcartbasic.cpp and another file right next to it called testshoppingcartdetailed.cpp, that throws a yellow flag.
Right. It's a heuristic filter to just narrow down the search space.
Yeah.
But you can't just delete the file yet. You move to phase 1, which is establishing a completely isolated, clean environment.
A sandbox, basically.
Exactly. The agentic tool has to ensure that the test suite can compile perfectly in its current state before it touches anything.
Which sets the stage for phase 2, where the real forensic science begins. The presentation talks about building a coverage baseline. How does this tool actually map those hidden pathways we were just talking about?
It uses established industry tools, specifically GCC, which is a compiler, and Gykov, which is a coverage analysis tool.
Okay.
When you run your test suite through Gykov, it generates a highly detailed map of your source code. It literally highlights every single line of code that the test executed, and more importantly, it highlights every line that was not executed.
Right, the presentation mentions looking for specific hash symbols, right? The little hashtag tag markers in the GCOV report.
Yes, those hash marks represent the uncovered lines. Imagine a developer looking at a massive document with 10,000 lines of code. Most of it is marked as covered, but those hash marks are flashing red lights.
Right.
They represent the dark corners of the application that no test has ever touched.
So phase 2 takes a snapshot of exactly where all those hash marks are.
Yep.
Then we move to phase 3, which is the surgical strike. The AI agent doesn't just highlight text and hit backspace. It actually manipulates the file system or the abstract syntax tree, the structural map of the code itself, to cleanly extract the suspect test file without breaking the syntax of the surrounding code.
Exactly. It's very precise. And once the suspect test is removed, phase 4 kicks in. The tool recompiles the entire code base and runs the GCOV analysis a second time.
So it generates a brand new map.
Yes, based on the new modified test suite.
Which leads us to phase 5, the ultimate deciding factor, the delta check. The source material stresses this golden rule. The exact set of uncovered lines, every single individual hash mark must remain identical before and after you remove the test.
Not the overall percentage, the exact specific lines.
I really want to dig into that because, if I am an engineering manager looking at a dashboard, I don't care about individual lines. I care about my overall coverage percentage.
Sure.
If I have 1,000,000 lines of code and my coverage stays at 98%, why should I care if the specific hash marks shifted slightly?
Because if the set of uncovered lines changes even slightly, it means that the test you just deleted was actually reaching a piece of code that no other test in your entire suite can reach.
Oh, so it wasn't a duplicate.
Exactly. It was unique. Even if your overall coverage percentage stayed exactly the same because the total number of lines shifted during the deletion, a new uncovered line means you just created a blind spot. The agentic skill is programmed with zero tolerance here. If the lines change by even a fraction of a percent, the tool instantly reverts the deletion and restores the test.
That level of mathematical strictness is fascinating, but it begs a massive question. If we are zooming in this closely on coverage and treating every single uncovered line as a potential failure point, isn't the ultimate goal to just push that coverage number to 100%?
You would think so, right?
Yeah. Why have any hash marks at all? Why not just tell the AI to keep writing tests until the dashboard says 100%?
Because aiming for 100% coverage is actually one of the most dangerous traps in software engineering.
Mm-hmm.
A metric stops being a useful measure the moment you turn it into a rigid target.
That sounds incredibly counterintuitive to me. I would assume 100% means the code is perfectly safe.
The presentation argues very strongly that mandating 100% coverage creates perverse incentives for both human developers and AI agents.
You know, it reminds me of the debate around standardized testing in education.
Oh, teaching to the test.
Exactly. If a school district decides that a teacher's entire career and funding will be judged solely by how well their students score on a multiple choice test, what happens?
They game the system.
Right. The teachers stop exploring interesting tangents, they stop teaching critical thinking, they just drill the students relentlessly on how to memorize multiple choice answers. The test scores go up to 100%, but the actual quality of the education plummets.
That phenomenon translates perfectly to software development. If an engineering team is mandated to hit 100% test coverage, the AI agents will start padding the stats to check the box. They will write hundreds of automated tests for trivial things, like basic getters and setters.
Okay, what is a getter or a setter in this context?
It's the simplest possible piece of code. A getter just asks the system for a value. For example, what is the user's name?
Okay.
A setter just updates a value. Set the user's name to John. There is virtually zero logic involved and zero risk of it failing. But if you test it, you get a quick boost to your coverage percentage.
Ah, so it's empty calories for the CI pipeline.
Exactly. Or worse, the AI will start generating fake assertions. We talked about assertions being tripwires, right?
Yeah.
An AI under pressure to hit a coverage metric might write an assertion that says, assert that true equals true.
Wait, it just writes a test that literally cannot fail.
Yes. The test runs, it passes instantly, the coverage tool logs the line was executed, and the percentage goes up. But it didn't actually verify any of the complex logic inside the application.
Oh man, there's a quote from the presentation that really drives this home. 100% coverage means you tested the easy stuff and skipped the hard stuff.
Because the hard stuff is genuinely difficult to test. Think about complex defensive branches in the code.
Like what?
Imagine deeply nested error handling logic that is only supposed to trigger if the central database crashes, the backup server is on fire, and the user's network drops all at the exact same millisecond.
Okay, yeah.
Writing a test to simulate that exact disaster scenario is incredibly time-consuming. So if a developer is chasing 100% coverage, they might just decide to not write that defensive error handling code at all.
Wait, really?
Yeah, they delete the complex safety mechanisms just so they don't have to figure out how to test them, preserving their perfect coverage score.
That is terrifying. They're literally making the software more fragile just to make the dashboard look better.
Yep.
So if 100% is a dangerous trap, where should we actually be aiming?
The author advocates for living comfortably at around 70 to 90% coverage.
Okay.
You focus on risk-based, boundary testing, you leave the trivial stuff alone, and you purposefully leave room for those complex error handling branches that might never get hit during a routine test, but will absolutely save your company from a catastrophic outage in the real world.
Right.
One complex test that covers 3 dangerous logic branches is infinitely more valuable to a codebase than 50 trivial tests covering one safe, happy path.
Wow. Okay, we have spent a lot of time on the theory here. We understand why AI inherently hoards redundant tests. We understand how the strict Phase 5 mathematical checks the DEDUP workflow safely remove them. And we know why chasing 100% coverage is a fool's errand. But, you know, theory is cheap. Does this agentic skill actually work on a live code base without accidentally deleting the whole project?
It does. The presentation includes the hard data from real-world applications. The author ran this complete DEDUP and gap fill workflow across 4 different open source projects, analyzing 52 source files in total.
Okay, let's start with the best case scenario for deletion. In the fraction subheap project, the AI tool identified a massive file called testfracgaps.cpp.
Yes.
It ran the file through the isolated Phase 1 sandbox, mapped the baseline in Phase 2, surgically removed it in Phase 3, and then hit Phase 5. The strict mathematical check proved that the file was entirely subsumed by other tests.
It was pure, unadulterated bloat. The system safely eliminated the file, dropping 59 redundant assertions from the CI pipeline forever.
Wow.
And the ultimate proof that the logic held up. The overall coverage stayed at a highly effective 98.06%. And the exact same 6 individual lines of code remained uncovered before and after the deletion.
That's incredible.
Zero loss in safety, but a permanent reduction in the weight dragging down the CI pipeline.
And in another project, digraphs APP, the system found literal copy-paste scenarios. It found triplicate test cases for a component called a min parametric solver that were identical down to the letter. It just mathematically proved their redundancy and nuked them.
Exact.
But the case study that really caught my attention was the Algo CEPA project because the workflow did something completely unexpected there.
Yeah, this is fascinating. In Alago CPP, the system ran its phase 0 heuristics and its phase 2 baseline and realized there was absolutely no redundancy to delete.
Okay.
But because it was methodically checking the Jaikov baseline, it discovered a massive glaring coverage gap. An entire component, a complex mathematical class called L1D, had absolute zero test coverage.
Nothing.
Nothing. The original generative AI agents had completely missed it during their initial uncoordinated runs.
So the system realized it couldn't delete anything and instead flipped into gap fill mode. It dynamically wrote 12 brand new tests, specifically targeting those complex mathematical branches, taking the coverage for that crucial component from 0% to 100%. So if we step back and look at the final tally across all 52 files in all 4 projects, what was the actual net result?
The net gain was exactly 2 tests. They added 12 critical safety nets in Allow-Go creeps and removed 10 redundant pieces of bloat across the other projects.
Wait, I have to stop you there. We just spent this entire deep dive talking about a tool designed to reduce bloat, and you're telling me the final result is that the code base actually got bigger. Doesn't that defeat the entire purpose of the DEDUP workflow?
It doesn't defeat the purpose, it elevates it. Systematic maintenance isn't just about shrinking a code base to make a number on a spreadsheet look smaller. It's about optimizing the signal-to-noise ratio.
Okay, explain that.
By ruthlessly proving which 10 tests were just dead weight slowing down the compute pipeline, the team freed up the resources and the visibility to add the 12 tests that actually matter.
Ah, I see.
You want your automated CI factory floor spending its precious compute power, validating the tricky, dangerous edges of your software, not running the same basic addition test 50 times just because an AI had prompt amnesia.
That is a phenomenal shift in perspective. The agentic skill isn't just a trash collector, it's a high-level editor refining the raw output of generative AI.
Yes.
Which brings us to why you, the listener, should care about this, even if you never plan to write a single line of C++ code or look at a GCOV coverage report.
Definitely.
We are living in a moment where the generation of digital content, whether it's code, text, or data, has become essentially free and instantaneous. But because it is so easy to generate, the uniquely human skills of curation, editing, and mathematically verified dilution are quickly becoming the most critical and valuable skills in the world.
There really is the ultimate takeaway here. We just walked through how incredibly difficult it is to safely delete a single redundant logic test. We had to build a complex, multi-phase agentic tool just to mathematically prove, via strict execution paths, that the deletion wouldn't break the system.
Right, because AI natively possesses that additive reflex and cross-session blindness.
Exactly. Now scale that mechanism up. What happens when we start allowing AI agents to generate and deploy automated logic pipelines across our real-world infrastructure?
Oh, wow.
I'm talking about AI building automated supply chain routing logic, or enterprise financial trading algorithms, or the automated power balancing sequences in a smart city grid.
Systems that actually execute logic and control real-world outcomes?
Yes, as AI instinctively bloats these massive infrastructure systems with overlapping redundant logic paths and unnecessary automated loops, we won't be able to easily isolate them in a phase 1 sandbox and run a phase 5 validation check.
No, you can't just reboot a city grid.
Right. Will we have the compute power or the oversight to painstakingly untangle and mathematically verify the removal of redundant logic in a city's power grid? Or will our automated infrastructure just slowly suffocate under the invisible weight of its own bloat until it inexplicably grinds to a complete halt?
That is a chilling thought. If we don't start building these rigorous, mathematically sound maintenance workflows into our automated systems today, we might all just be sitting around staring at a spinning wheel, waiting for infrastructure that is too bloated to function.
Definitely a real possibility.
Well, definitely something to chew on the next time you marvel at how fast an AI can generate a solution. Keep an eye on those hidden redundancies. Until next time.